Hello again. Yeah, I'm Eric. I work on Android web performance in Google's London office. And to give you sort of a setting the stage moment, what I want to talk about is how we made it possible for Chrome on Android to double its speedometer performance in the last 2 years. It's a pretty impressive achievement. And before we go any further, I'd like to say thank you to everyone that contributed. This was an effort that really spanned a lot of teams across the stack, not only in Chrome and in the industry wider, but also down to the hardware level in companies like ARM and Qualcomm, and into the system software stacks and Android and the Pixel team. So yeah, I want to basically go into this timeline. How did all these changes that we made stack up to a 2x improvement? I want to geek out a little bit about a particular improvement in build optimizations, show you some profiling data there. And then if we have time, I'll talk a little bit about tooling and some of the other CUJs beyond speedometer that we're looking at in the future. So yeah, talking about this timeline, 2x, right? There are 3 areas that these improvements came from. We'll go into them one by one. The first one are build improvements. These build improvements really are the fundamental change that's happened over the last 2 years. The thing that enabled all of this is that we ended up splitting a separate build from Chrome's regular APK on Android that was targeted specifically to high-end Android devices. As you guys probably know, Android is like a really diverse device ecosystem. And shipping an app on Android means you have to ship an app that works well on the high end, but also on the really low end, devices that have only little cores, that have very limited amount of RAM, and have also have flash that's very poor and very small. And so binary size is a huge concern for those low end devices. And that's why Chrome's build traditionally over the last decades has always been optimized for size rather than for speed. Now, we actually have phones in our pockets. Most of us will have phones in our pockets that are basically as performant as our laptops in single-threaded performance. And that changes the game. I think we have enough resources available on those devices that we really should be shipping a high-end configuration of Chrome to them. And that's exactly what we did. So we made a build that replaces optimizing for size by optimizing for speed. We targeted ARM64 instead of ARM32, and we started using PGO profiling, which is basically an optimization that it profiles, it runs Chrome with instrumentation added to it, and then it tries to understand which is the hot path through all of Chrome. Let's optimize that one in particular. That change was the first sort of step change for us. That was a 20–30% improvement. For the device we're showing here, that's a Pixel tablet, it's probably more on the higher end, 30% upwards. After we realized how important that was, we spent more effort into optimizing this build further. We realized that actually we can tweak the PGO profiles. We can make sure that PGO profiles are generated on code that's as recent as possible. That means that they have more fresh and they are more targeted to the actual binary that we ship in the end on our release branches. We also made sure that the profiles are generated on the real hardware that we want to ship on. So we use Android ARM64 high-end devices to profile and to create these PGO profiles. Those changes stacked up to another 10% or so. We looked at inlining. We made sure that some of the changes that were made specifically for Android's low-end build in Android's configuration were disabled, were reverted back to something that looks a lot more like desktop Chrome. That's disabling the machine learning inliner. This is actually an inliner that tries to optimize for size. Isn't really called that, but turns out that's what it does. We replaced that inliner eventually with a new model of the inliner, of the ML inliner, that only targets cold code. So the cold code inside Chrome's high-end build is still going to be optimized for size, which means that we can reduce memory footprint too, and that actually gives us another little uplift. We also increased inlining in more general ways, both within modules and across modules. Finally, there's another optimization on top of PGO that we employ on Android. PGO is all about optimizing the code within a function. The order file is all about, we have lots of functions, let's make sure that we lay out these functions in a sensible way in the Chrome binary. So we made sure that we are also using relevant builds to generate these order files. And we made sure that those order file instrumentation, that order file instrumentation also works well with the prior changes to inlining that we landed. All of that together is probably responsible for about half the uplift in performance over the last 2 years. The majority of the other half comes from the cool work that all of you guys are doing on the browser and on the rendering engine. And it's JavaScript engine. There were a couple of changes that were, particularly worthy of calling out. There was one change that enabled a fast path parser for inner HTML parsing. It turns out that's actually really important for speedometer performance. So doing that led to 5%. We shipped 2 new compiler tiers on Android over the last 2 years. First, we shipped Sparkplug, which is sort of a super fast compiler that spits out pretty poor code, but it does it very quickly. And it's an improvement on top of Ignition, our interpreter. And that, again, another uplift of 6%. And then there were so many little changes to parsing, text rendering, style layout, etc. The rendering engine really played a big role in the uplift too. Finally, some changes that recently landed target GC timing, and GC timing is important for speedometer because you really want to make sure that GC happens at the right time so it doesn't affect the speedometer score. Last area, scheduling. So speedometer is really interesting from a scheduling perspective. In theory, it's a benchmark. In theory, it should just be a very continuous workload. And continuous workloads are really easy for schedulers to deal with. They can just ramp up CPU to the maximum, place that big workload on the big core, and be done with it. Not so speedometer. Speedometer is a workload of very many little tiny tests and has idle phases in between those tests because we have to make sure that the frameworks do all the relevant work required for the subtest. So we schedule repos animation frames to give the web frameworks a chance to do all that asynchronous work. But scheduling RAFs means that we'll wait for the next vsync. So we'll add in a little bit of a delay. And suddenly it doesn't look like a benchmark anymore to the scheduler. So I think there's still a lot of opportunity to improve scheduling further for speedometer. But we've done a few things for Pixel specifically to flag the important threads as really critical ones during the speedometer execution. And that led to a little uplift too. Other OEMs, other Android partners are doing similar things in their scheduling layers to make sure that speedometer works well. All right, next, build. So what I really want to talk about is how do all those changes help? Especially how does PGO help? And maybe also what can we learn when we look at the hardware performance of web content? And how can we make sure that that ecosystem then thrives from those insights? So the main fundamental piece of technology we're using for all of this is Perfetto, and we combine that with perf profiling. Here, we're basically breaking down where are the CPU bottlenecks for different speedometer subtests. We look at some stall counters. Those are basically cycles that the CPU had to be waiting to make progress because it was waiting for data from somewhere, or because it had to crash the execution and restart it from scratch. The insight that we saw here is that actually the stall rate, the number of cycles that had been spent stalled as opposed to making progress, is really high in speedometer, higher than in many other benchmarks that CPU architects might use. Part of the reason for this is that speedometer has a lot of branches. Speedometer's branch count is about double that of other CPU benchmarks like Geekbench. And branch mispredicts are really costly. When you have a branch mispredict on an ARM CPU, that means that you probably also pollute your caches. The cache hierarchy on modern CPUs often takes branch prediction into account and prefetches data that it thinks it will later need to execute code in the branch that is the likely one to be taken. It will prefetch that data into lower level caches so it's available quickly. If you have a lot of branches, the branch predictors cannot work as effectively. Every branch takes up space in the branch target buffers. And yeah, that ultimately means speedometer is more front-end bound. Now, there is one thing that you can do to avoid having branches taking up space in the branch target buffer, which is to make sure that most of the time the block, so the path through the branch that is being taken is the one that is the fall through path through the branch. So you encounter a branch instruction, you want to make sure that most of the time it doesn't actually branch. Most of the time it goes straight to the next instruction. Those branches that are likely to fall through, they don't take up space in the branch target buffer. And that's exactly where PGO comes in, right? PGO helps us optimize that behavior. There are, of course, also other insights that you can gain from this. And I think the partners that we're working with, they're very happy about those insights, which is basically that, this front-end boundedness and this high number of branches in speedometer makes for a really interesting workload for CPU architects to make sure that, actually let's build some CPUs that have large enough front ends to deal with all of this. So yeah, with PGO enabled, the data before that I showed you here, this is from M120, so this is PGO not really optimized yet, but already high-end build for Chrome. So now we're moving on to M128, the more recent build, where we have actually optimized PGO. What we see here is that the bottleneck moves from the front end to the back end. With PGO, we reduce those number of the number of taken branches, and we increase the number of not taken branches. And that relieves some of the pressure on the front end. The other thing that happened here is that we moved CPU generations. We moved from Cortex-X3 in Pixel 8 to Cortex-X4 in Pixel 9. That's a larger, big core with a bigger front end that also contributes to this move to the back end. Order file also improves on this, but through a different mechanism. Order file helps us reduce TLB misses on the instruction side. And these backend stalls that are remaining now, those are really the thing that we want to look at next. Those are that's where, sorry, PGO and build optimizations won't really help us anymore. Backend stall is mostly influenced by data accesses. So what are we loading, rather than what code is it that is executing. We started looking into this, and one of the insights here is that for stalls overall, most of the stalls in this generation of CPU are coming from L2 misses. Most of the time, we actually have to go to DRAM, and that's half of the stalls in Cortex-X4, almost, just under, that are due to this. So what can we do next to make progress there? We are using profiling technologies, tools, perf, simple perf, and Perfetto to attribute those L2 misses to code in Chrome. We can even use some more advanced technologies that ARM chips provide, like a statistical profiling extension and a tracing subsystem that allows us to record instruction traces, to attribute those L2 misses and those stalls to instruction sequences or individual instructions. And then dig deep into why might there be a bottleneck in those. That's work that's just starting, and it's hopefully then going to enable the next, I don't know, I won't promise doubling of speedometer score, but next improvements. So yeah, briefly to talk about tooling. Fundamental to all of this is Perfetto and Perfetto's integration with Chrome. Perfetto is a tracing daemon that runs on Android and provides a lot of insight into what the system is doing. We can combine that with profiling data to align timeline data and profiling data and create all these nice breakdowns that you've just seen. Yeah, we're doing this by basically breaking down speedometer execution in those traces into different little phases. And if you've seen my talk just now, you will have seen some of this instrumentation in action. Yeah, it basically helps us understand, well, where is specific subtests of speedometer? Do they have different characteristics than other ones? What can we feed back to, say, the V8 team or the Blink team to optimize in each of these? You can align this data with perf counters, like the instructions and CPU cycle counters. This helps us understand and identify where are there stalls, where's low IPC. And you can align it also with stack sampling. And this is where we can now attribute to code and understand where's slow code. We can also try and align stack sampling and PMU data to identify other particular stacks that have particularly poor IPC. And then we have low-level data sources like ETM and SPE. Those are the two that I just talked about. We also integrated those with Perfetto's tooling. And the example here shown is that there are some instructions that actually have really poor IPC. So here we're having an instruction range of 4 instructions, and it took 300 cycles to execute it. That's not really good. And down here we have a single load that has also, this is a load. We have a data address and a physical access. We also have a frame, so we can identify the piece of code that is responsible for this load. And we see that that's an instruction that had to go to DRAM. Now, looking at that instruction stream is going to be complicated, right? That's a lot of data for us to analyze. This tooling helps us aggregate it and present it in different ways. So we're very excited about the insights we might be gleaning from this in the future. Yeah, finally, let's talk a little bit about workloads beyond speedometer. We've got a lot of CUJs that we care about. And I think this graph kind of tries to show where do different CUJs exercise the browser's components, and which of those components are actually critical for the score that's ultimately computed or for the user experience metric that's relevant. And I think you can see that speedometer is relevant, right? Like there's some overlap with page load. There's also, speedometer is an interaction benchmark. There's overlap with interactions too. But there are components that page load exercises that speedometer doesn't. The same goes for scrolling. Scrolling actually is quite different from speedometer. Scrolling's critical path really involves the graphics and input pipeline, not so much the renderer main thread. Chrome has traditionally relied on field data for those areas. We've got good metrics that work well at scale, but in all of this work and these kinds of optimizations that we're doing here, we're talking about vertical optimization. Field data doesn't really work for us. We can't easily run experiments in the field to tweak pixel scheduling or see, well, let me build 2 different CPUs and see which one performs better. It's quite expensive. So really what we need is more lab workloads, and that's why we're investing into building this out. We have a first benchmark available for you to try and give us feedback on. This is a new page load workload, I'd say, that tries to use a small subset of websites to build a generic picture and hopefully a representative picture of page load performance in the lab. That's all I have. I'm happy to answer any questions.
Right.
Hi, thanks for the cool talk. So profile guided optimization applies to the browser's C++ code.
Correct.
Can you talk about like the runtime profile information that V8 gathers and how it uses it to generate good code, good JavaScript generated code?
Yes, to a degree. I mean, if we have someone from the V8 team here, they might be better to talk about that. But yes, I think for V8, the compiler tiers work quite well. That's our impression, at least. The improvements that we saw earlier, for introducing Sparkplug, introducing maglev, they help. The thing that is tricky for V8 specifically, I'd say, is that it depends on how fast you can run the compilation, right? How good of a code you generate.
Oh, okay.
You were saying there is a thing that V8 does where we have. Oh, sorry, I'm Adam from the V8 team. So C++ code is what the PGO stuff does, but V8 has its own PGO pipeline for code that we generate ahead of time, like our built-ins that we generate from code assembler. So we do get some of that same benefit for anything that we needed ahead of time. Yeah, the answer about tiering is correct for JavaScript code out there, but I just wanted to say there is additional work for like V8 runtime code that doesn't happen to be written in C++ that still gets a PGO bump.
Hi, Dan on the PWA team for Chrome. A long time ago, I worked on storage, and I remember we struggled with some perf tests for things hitting disk. One area that was a big struggle was measuring startup. Like we were like, oh, like startup time is bad, but as you can probably imagine, opening a database from disk on startup, especially, it's so noisy, it's very difficult. I was wondering if in the new, I forget, was it line break?
Load line, yes.
Load line. If you incorporated some storage APIs, because I do know once it was warmed up, it was fairly not noisy. And if you've incorporated like IndexedDB or any of the modern storage APIs into those benchmarks.
Yeah, I believe that's one of the features that we looked at. I'm not sure if in the ultimate selection it ended up being represented well. We've got currently load line is kind of a benchmark that targets Android devices. We've got two configurations for it, one for mobile devices and one for sort of more tablet style Android devices. That segment of Android is still growing, right? We do expect more heavy usage there. But what we really want to do now is extend this also to real desktop usage and more productivity apps who use storage more thoroughly. So the one productivity use case that we currently have in our story set is Google Docs. I'm assuming there's some storage usage, but I'm not sure what exactly it utilizes.
Wait, hold up.
I believe the usage is only there if you enabled offline docs.
Right.
And that is, I think we do have the only perf test, I think there might be a couple, but one of the perf tests for IndexedDB is modeling Google Docs, the offline load. So I just like manually looked at the traces. It took a long time and just like, I'm just going to do exactly that. And it's caught a bunch of regressions, which is nice. But I know that IndexedDB usage is pretty high, and I'm sure it's used a bunch on mobile. And I know at one point other vendors were faster than us at the IndexedDB, but we didn't really have any tests. So I'd love to see it incorporated into something
let's
here.
work together on it. Absolutely.
Hi, Ian from the Blink team. Super cool. Myself and a few other people would love to look at the stalls, I suspect, when you've got that more widely available. Would it be true that, like, if you get a stall initially, then like you might not see it, and like, you know, subsequent, you know, like say you're loading something into from cold memory and into like an L1 or L2 cache, and then subsequent accesses are really fast. So it wouldn't necessarily, like, targeting top stalls wouldn't necessarily like help that much potentially. Is that a correct assumption of the
I
world?
think you always have to look into the context around the instructions that are stalling, right? Oftentimes it's, as you say, right, something is actually being evicted out of the cache by something else that ran before. So the problem isn't really in the stall, it's about what happened before. And you know, that the same goes for branches, right? Sometimes branches get mispredicted. Maybe that's because something threw off the branch prediction beforehand. Maybe that branch was evicted out of the BTB, things like that.
Hi there, Howard from Edge. I was just curious if the PGO that you're doing that's targeting speedometer, is that the same PGO that's shipping to users? So is that speedometer usage mapping to user usage? Like, are you optimizing for the right thing for users?
Yeah, that's a very good point. For Android at the moment, PGO uses a number of different stories. Speedometer is one of them. We also incorporate other benchmarks like MotionMark or Jetstream. We also look at some of our system health metrics and system health benchmarks. I think we'll try to integrate load line in the future too, as like a page load workload. I think there's more coverage that we could add for this. There are some other optimization opportunities. We want to look into AFDO, which is basically field collected data to see what actual real user stacks and paths through the binary look like, and use that to optimize. But that requires a bunch of inference investment that doesn't currently exist, at least not for Android. So I think all of this is kind of you have to evaluate what benefit this brings, how much it will cost you to get there. But yeah, today speedometer is only part of the stories. I think that's why we think it probably works well. Ultimately, we looked at field data also to see the impact of some of the changes that we've made, and yeah, so far this is definitely a positive change compared to no PGO or compared to PGO that doesn't include speedometer. All right.
I think that's it. Thank you, Eric.
Thank you.